se realiza el día de hoy porque tenemos un visitante importante y pues agradeciéndoles a todos su participación durante el año. Va a haber cambios de nuevos organizadores en el coloquio, ya lo sabrán el año que viene. Muy bien, bienvenido Ignasi Ribas.
Gracias.
Él es doctor en física por la Universidad de Barcelona y actualmente es profesor de investigación en el Instituto de Ciències del Espacio del Consejo Superior de Investigaciones Científicas CSIC. También es miembro del Instituto de Estudios Espaciales de Catalunya, IEEC, el cual dirigió del 2017 al 2025. La actividad de investigación de Ignasi Ribas se centra en el descubrimiento y caracterización de exoplanetas, en particular aquellos que son similares a la Tierra, para buscar vida en el futuro. Tiene responsabilidades de alto nivel en instrumentos astronómicos, así como en diversas misiones espaciales, entre las cuales Keops, PLATO y Ariel. Coordina además el desarrollo de proyectos de nanosatélites. Ha publicado más de 500 artículos de investigación en revistas internacionales de alto impacto. Recibió el Premio Ciutat de Barcelona en Ciencias Experimentales y Tecnología en 2018. El asteroide 667531 Ignasi Ribas lleva su nombre. Bienvenido, muchas gracias. Adelante.
Muy bien, muchas gracias por la presentación. Ante todo, disculpas porque estoy fatal de la voz, voy a hablar bajito y a ver si me aguanta durante toda la conferencia. ¿Vale? Bueno, como decía, gracias por la invitación, es un placer estar aquí, un placer enorme. Voy a dar la plática en español. Si es algún problema... You prefer English? ¿Todo el mundo
We have
okay?
postdocs.
Okay, no problem.
Problema?
I can do English, no problems at all. Okay. All right, so my goal here is to give a overview of what we're doing today, what we know to the exoplanets and what we're doing to prepare the future, let's say, and what we expect from future research in exoplanets. So one thing that we have learned over the past 30 years, remember that this year was the 30th anniversary of the first exoplanet discovery around the normal star like the sun. So it was October. And one thing that's changed our perception of the universe actually is that, oops, let's see if this works. Yeah. Okay, that's a bit slow. Anyway, that's how we see a starry night, let's say. This is a very dense field, somewhere in the direction of the galactic center. You can see lots of stars, and what's changed in the last 30 years is that now you have to realize or imagine that we're actually seeing these, right? So each of these stars, most of these stars, not each of them, but most of these stars has a planetary system around it. So we know now that exoplanets are ubiquitous in the galaxy. They're all over the place, and they're very, very common. And this is one of the major results, I think, in all of science in the last 3 decades or so. So how did we get here? So let me just quickly go through how we detect exoplanets and why it's, let's say, difficult, because the methodologies we use are quite inventive, let's say. And the main issue here is that because of a contrast problem, we cannot, in general, directly image exoplanets, but we have to detect exoplanets indirectly by measuring how they change their star, by changing the position, the velocity, the brightness, or other phenomena. So it is possible to take pictures of planets, direct imaging, but this is a minority of the planets that we're observing, and it's only possible for those that are extremely bright compared to their star and very, very massive, usually very, very young. So, but most of the techniques that we're using are the so-called indirect methods. And as I mentioned, Doppler techniques are common, and this is the one that was responsible for the first exoplanet detected using around a normal star transits. I'm going to address that as well. Here in this room, we have a pioneer of one of the techniques here is the astrometry. So some of the detections have been made from this very institute here. This is about measuring position changes. And then they can also be, one can also find exoplanets by measuring timing or using other more fancy or, let's say, specific techniques like gravitational microlensing. All these are encircled or enclosed in the red line are indirect methods. And that's the majority of our discoveries have also actually been made using these kinds of methods. But this is a lot more complex than this simple diagram. This is a well-known diagram from Michael Perryman. This is updated as of about a year ago. And then you can see that there's all this sort of octopus-like shape. This gives some indication of how different methods work and how far they go into smaller and smaller planets. Of course, it's a lot simpler to find massive planets, right? Because or big planets around their stars because the effect is larger. And therefore, the goal here is to go smaller and smaller. And different techniques allow us to go deeper, let's say, or smaller in this diagram. And you can see here, some of these branches go really far down, and this is one Earth mass and so on. So you can see there's a huge variety of exoplanet detection methods, indirect detection methods mostly. And this is because we have astronomers usually come up with methodologies to actually see or to detect, not see, but to detect indirectly the effects of planets on their host stars. Now let's start with the radial velocity method here. This was pioneered in the late 80s from last century. And it's about measuring velocities, radial velocities. So that the indication there is that when we have a star that has a planet around it, of course the star will also have a reflex motion as the planet orbits the star will also move around the common center of mass, the barycenter. And then that means that the star will be periodically coming towards us and away from us. And this is measurable through radial velocities. Now, the problem is that these motions are tiny, right? So we take the solar system here, we take the different planets, the period in years, and the semi-amplitude in meters per second, and you can see the numbers here. This is Mercury, Venus, Earth, Mars. So Earth induces a 1-year radial velocity wobbling motion on the sun, which has an amplitude of 9 centimeters per second. So to detect Earth, you have to keep observing the sun for a few years at least, and to be able to see a tiny modulation with an amplitude of 9 centimeters per second. This we cannot still do. So this is beyond our current technological capabilities. What we can do is to detect planets like Jupiter, for example. This 12-year period, and the semi-amplitude is 12.5 meters per second. So this is now possible, actually. And the first exoplanet was indeed a Jupiter-type planet, actually Jupiter mass planet, but not a Jupiter type planet, because this Jupiter mass planet is extremely close to its host star. And that was a big surprise. And that also opened up the idea that maybe planets don't form where we see them. They actually form elsewhere and they migrate in their orbits. And this on the top right, this is the discovery radial velocity curve for the first exoplanetary normal star. So this plot here is worth a Nobel Prize. So this was the discoverers of this, Michel Mayor and Didier Queloz, were awarded with the Nobel Prize in Physics in 2019 because of this wobbling motion found around 51 Peg that shows that this star has half a Jupiter mass planet around it. So you can see one also important thing is that radial velocities don't yield the actual mass, they yield a lower limit to the mass, right? Because it depends on inclination angle, it's a projection, and therefore what we get there is an M planet sin I. And so depending on how sin I, whatever number we have, then it can be actually much larger than the masses than the minimum mass of the planet. Now, this radial velocity method is enabled by incredible machines that are precise radial velocity or precision radial velocity instruments, spectrographs. And these are machines that are super stable, enclosed in a vacuum chamber, and then kept there for as long as we can without touching them, so that the stability is not broken. And one such instrument is the CARMENES instrument, which is mounted on the 3.5-meter telescope in Cala Alto in southern Spain. And this was built by a consortium of Spanish and German institutions, and the consortium has been having lots of telescope time, which is extremely good, and we're very grateful to the observatory. So more than 1,200 nights of observation, which is a lot, actually. Now, this instrument has 2 channels, a visible channel and a near-infrared channel. You can see here, these are the vacuum chambers, and they're enclosed, like say, in the so-called Coude room. So they're completely preserved there, away from the telescope, away from anything else. And the light from the star and some calibration light is fed through fiber optics, so fibers, right? And so those fibers bring the light of the telescope. There's an optical bench in the vacuum chamber, and then with the grating and everything, and the detector and so on, and that registers the spectrum, and then can be downloaded and processed. So as I say, this has two different channels, visible and infrared. So visible, this coverage, and the infrared there, and it's especially aimed at surveying M-dwarf stars. So talking about the low mass end of the main sequence, that's where this instrument has its prime, because it's red optimized, let's say. So it's optimized to observe objects that emit mostly red light. So now I'm going to show you a few slides of the CARMENES results, and because I'm the project scientist and now the PI of one of the projects as well. So we've been deeply involved in that. Now, as I was saying, we are homing in on M-dwarfs, right? So we're talking here this diagram shows the stellar mass, stellar host mass, and the y-axis is the planet mass in Earth masses. All these little symbols are measurements from the literature, and those that are colored are results from CARMENES. As you can see, most of the previous surveys and most of the surveys have been focusing on stars that are between 0.8 and 1 solar mass, while with CARMENES we've been extending this all the way down to even as low as 0.1 solar masses. By the way, this diagram shows only RB discovered planets. There's many more from transits, but this is planets that have been discovered using RBs. And actually, half of all known RB planets with stellar hosts that are below about a fifth of the solar mass have been discovered by the CARMENES instrument, which is extremely efficient. And there's been a zoo of planets found: Neptune's enclosing orbits, eccentric planets, active stars, and so on. So there's a lot of results from CARMENES, and we now have like about 140 papers coming out from the CARMENES survey. So it's quite successful as well. Now, I think everyone has a favorite star, and this is my favorite star. This is Teegarden star. Teegarden is a tiny little star, 0.1 solar masses approximately, which is moving really fast. It was only discovered a few decades ago by Mr. Bernard Teegarden, I have to say. And this star is amazing because it's super tiny. It's an M7. It's the closest M7. And it has at least 3 planets. So with CARMENES, we have been observing this a lot. And we have found a number of planets. By the way, it's very close as well, 3.8 parsecs, so it's really around the corner, literally. And the planets that Teegarden star has, you see, 1.1 Earth masses, 1.05, 1.8. So these are really 1 solar mass planets, 1 Earth mass planets around these stars. And even more, some of these actually have, they call it installations, which means, or insolation, let's say, which is very similar to the Earth's insolation, which means that they could potentially be habitable in terms of planet radiation, let's say, or the radiation that comes into the planet. So it's an amazing system, and we keep on observing it, and probably there's more planets. We have hints of another 2 more planets in this system. Now, one of the big surprises here is that with CARMENES is that we were not expecting many giant planets. Models don't predict giant planets around M-dwarfs just because the disk mass is not enough, it's not sufficiently dense, let's say, or high to form planets of high mass. And we have indeed found quite a number of giant planets around these M-dwarfs. In some cases, even around tiny M-dwarfs, which was a big surprise. And it's not spurious. You see here the detection curves of one of these systems. They're super easy, they're super obvious. There's no question that this star has 2 planets, a long period here and a shorter period there. So there's no question about that. And when we go and compare with state-of-the-art models, and all these little dots here are mock planets found with state-of-the-art planet formation models. This pebble accretion model, which is what's being developed these days. This is, in this case, from Remo Bern. And then all these colored stars are the planets that we have found with CARMENES and other surveys as well. And why? When we focus on point solar mass stars and the likes, there's a few of these dots that happen to be around the star, so it means that maybe a few planets can be formed. When we go down to 0.3 solar masses, there's a lot less. It seems that maybe not, actually. So it's very unusual to find these many massive planets around here. And when we go to 0.1 solar mass stars, these 3 planets that CARMENES has found are sitting way above the distribution of these dots, which means that the models cannot explain the existence of these planets. Now, probably you could say, well, the models are wrong. Well, they're wrong in the goal of explaining these kinds of planets. Probably there's a shortcoming to the models, meaning that the formation channel for these planets is probably not the core accretion or the pebble accretion channel, but something else called disk instability, so direct collapse of the gravitational or of the protoplanetary disk. So this is actually, in a way, revolutionizing planet formation around these very small stars, because we see evidence that planets form in a different way than the rest of the planets, the less massive planets around the stars. Right? And the last result I wanted to share with you about with M-dwarfs is that also we have enough statistics. We are monitoring about 350 stars, and there's enough observations, and now more than 25,000 observations that we have to get occurrence rate estimates. So how many planets we have per star. And it's actually quite amazing to see that we have 1.44 planets per star. So that means that there's lots of planets around those stars, and in most cases there are multiple planet systems. 94% of the stars that we have surveyed have planets, which is almost 100% of them. And this famous Eta Earth number, which means how many of those planets happen to be in the habitable zone when with the right mass, let's say, it's about 30% or so. Right? So this is the number we have. We also found this, as I mentioned, this excess of giants around these guys. And then I think one result that is really recent, and I like it a lot, when we home in on the really, really low mass end of the main sequence, so planets, so stars that are less than about 0.16 solar masses, these are really, really late types, we find more than 2 planets per star in these cases. And it's almost 100% efficiency. So as soon as we keep observing them and we get to the right, let's say, mass detection limit, then we see planets in all stars. And we have run a number of experiments that have been always very successful. And the other thing is that you can see here, just this is, and it's a very steep mass function. So this is the occurrence rate of different periods, different orbital periods, as a function of planet mass. So this is between 0.5 and 3 Earth masses. This is between 3 and 10 Earth masses. And see that there's almost a factor of 8 to 10 more tiny planets than those, let's say, mid-sized planets. So these stars have 10 times more planets similar to the Earth than they seem to have planets, let's say, of masses of a few or several times the Earth mass, which means that they're extremely rich planetary systems and mostly formed of one or a few, let's say, Earth mass planets. This is really amazing. And Tiergarten star is one example. This is one of the examples there. And also TRAPPIST-1, which you probably know as well, is another example of these rich planetary systems at the very end, a very tail of the main sequence. So what is the state of the art in terms of precision RBs? This is a very good example. You know, Proxima Centauri has already a few planets being announced. The first one was Proxima Centauri B by Englada Scudé in 2016. Now these observations were great with HARPS. Now it has been superseded with ESPRESSO. ESPRESSO is capable of precisions of order of a few tenths of centimeters per second, which is absolutely amazing. And you can see here this is the same curve. This is HARPS curve, and this is the same target, the same modulation of Proxima B with ESPRESSO. You can see the improvement in the quality. And also there's Proxima D here, which has an amplitude in velocity of only 35 centimeters per second. So we're able to find, or they are able to find, planet modulation of order of a few tenths of centimeters per second, which is absolutely amazing. Now, if we move on to different detection method, that would be the transit method. This is very simple. If we have an edge-on system, so that our visual is perfectly aligned with the plane of the orbit. Every time there's one orbit, there's going to be an eclipse, so the planet will cover part of the star, and therefore this will produce a transit, which has a depth that is proportional to these surface ratios of planet to star. Right? In the case of Jupiter and the Sun, this is about 1 to 2% depth. independent. The bad news comes when we say that the Sun-Earth is about 80 parts per million, so that the transit of an Earth around a Sun-like star is super, super tiny, and which we still cannot do, actually. If we go to a bit more favorable case, so an M dwarf instead of a Sun and an Earth, then it's a lot easier, so that 5.5% or so, 5 millimagnitudes. And the nice thing about having radii, what you can determine from the depth of the transit, is that one can do a bit of planetology already, right? So we plot planet mass versus planet radius. We ask our theoretical colleagues to calculate with equations of states what would be the relationship between mass and radius, and you can see these curves here. Each of these colors identifies one different composition, 100% iron, 100% rock, 100% water, and some puffy planets. And you can already see here that rocky planets tend to be very low mass, that there's some intermediate cases where we have the Neptunes or some Neptunes and some super Neptunes, and all the very massive stars are puffy, are rich in gas, right? So we can have an idea of the bulk composition by just plotting this thing. So this is already quite well understood. And all this, let's say, abundance of exoplanets that we have right now are actually in many ways attributable to these transits from space. So there's been specific space missions tailored to observe stars for long time periods and with high precision, missions like Corot, like Kepler, like TESS and Cheops, and they've allowed us to have thousands of transiting planets that we can now study. The technique, the strategy is simple. You go out, you take a telescope, you point it to a star field, you observe over and over and over forever, as long as you can, right? So years, if you at a time you can. And without any day-night cycle, and you observe maybe a couple 100,000 stars, and you keep going. And that has, for example, Kepler K2 has contributed maybe more than 3,000 planets in transit actually to the lists. Let me just say a few words about Cheops. This was in the slide here. Cheops is not a survey mission, it's a planet follow-up mission. So it's a small telescope in low Earth orbit that is capable of doing a space precision photometry. And why I'm saying this here, because, well, I'm directly involved in Cheops, but also because everyone here could actually get Cheops time to get observations, photometric observations and photometric monitoring. This, as I say, is a 30-centimeter space telescope, which launched about 6 years ago. And the GEO program, the Guest Observer program, is open to everyone. And it can do pretty precise measurements in photometry in one band, which is a bit red. And it's, as you can see here, the noise level is only of order of a few tenths of parts per million in 1 hour. So it's really super precise. And one major discovery, for example, was this Nature paper by Rafaluque et al., HD 110067, which Cheops and TESS managed to discover a 6-planet resonant chain. Say all 6 planets having transits and a sequence of small number commensurabilities, which is amazing. Actually, the nice story about this is that some of the planets were found the same way that that Neptune was found in our solar system, by perturbations, let's say, from the other planets in the solar system. In this case, it was to keep this resonant chain. There were some transits missing in the TESS data and with the Cheops data, and then Cheops went and observed at the predicted times from this resonant chain theoretical calculations, and sure enough, the transits were there, and the whole system could be resolved, let's say. Now, in the future of transits is PLATO. PLATO is this mission from ESA. This is the so-called M3, and the PLATO mission, contrary to excuse me, to TESS and Cheops, will be focusing on Earth twins, so Earth-Sun twins, so trying to find Earth-type planets or Earth-sized planets around Sun-like stars. This is the main goal of PLATO. And for that, you see here, there's an optical bench with 26 telescopes, each pointing more or less the same area of the sky with the small shifts. And it's launched, is planned for about in a year's time, so end of 2026. And this will be also revolutionary because it has the chance to be able to find the first, let's say, exo-Earth, right? Which we don't have any exo-Earths just yet. The techniques are simple. We're talking about transit photometry, so try to see the little dips in light caused by planets crossing the star. But there's a big plus to PLATO, is that it can also do astroseismology, meaning stellar oscillations. And stellar oscillations, which are these oscillations that the star vary because they have sound waves bouncing around in their structures. Those sound waves, much like happens with seismic waves on Earth, allow us to probe the interiors of the stars. And therefore, from this astroseismology information, one can determine the mass of the star, the radius of the planet, and also the age of the star, which is a big deal because it's very tricky to find or to determine stellar ages, and to a very decent precision of about 10% or so. So with the PLATO sample, we will have very good determinations of the properties of the stars themselves, masses, radii, and ages, which also would enable us to do comparative planetology, right? So we can see how planetary systems evolve by taking snapshots at different times of similar planetary systems, for example, which is going to be a major step forward here. Now, the PLATO mission will observe about 250,000 stars. There's going to be a core sample and a statistical sample, plus a number of M-dwarfs. And the first field of PLATO, which will be observing starting next year, that's in the south. You probably have heard about Kepler. Kepler had a camera of about 100 square degrees. One single shot was 100 square degrees on the sky. PLATO is 2,100 square degrees, so 20 times larger field than Kepler, which means that we have maybe a few more stars, not that many more, but this means that stars will be, on average, a lot brighter, and therefore we can do follow-up on them, which Kepler, that was problematic. And you can see the field here. Some areas are covered with 24 telescopes, some with 18, some with 12, some with 6, and these will be observed throughout the mission, which will last for about, I think, 6 years or so. Now, what do we know after these years about exoplanet demographics? So what we know about the distribution of planets, and that's going to be very interesting. This is a plot that I use a lot, and there's a lot of discussions on this. This is orbital period of the planet as a function of planet mass here. Of course, we see the pictures of our solar system planets there. And each little symbol is one exoplanet discovered by these different techniques, right? So transits, RBs, timing variations, imaging, and so on. And there's 6,000 exoplanets in this plot, which are roughly the ones that we have discovered up to date. And you can see lots of very interesting features in here, which I won't have time to discuss, but this would be our Jupiter-like planets, so massive, so high mass or giant planets in orbits around stars with periods of thousands of days, let's say, several years. There's also the hot Jupiter region here, so Jupiter-sized or mass planets in orbits very close to the star, periods of only a few days. And there's sort of nothing in between, and this is a sign of planet migration. Sometimes you have to stop planet migration somewhere, and there's an empty area here. Same with, if you go to masses, Jupiters are quite common, and so are what we call sub-Neptunes and super-Earths, but their masses in between, let's say about a tenth of a Jupiter mass, are not that common. So there's also a lot of information in this diagram as to how planets form, and then any model will have to explain this, right? And of course, there's one very strongly striking feature in this plot, and is that there's no little dots where we are, right? There's no symbols where the Earth is sitting, which means that there's no exo-Earths so far. And the reason there's no exo-Earths is because it's a strong, let's say, observational bias. We are a lot more efficient finding massive planets, preferentially in close-in orbits, than we are finding small planets in wider orbits. And therefore, we expect that as techniques keep improving and we keep having more and more super precision photometers in space and also instruments on the ground, this will be gradually filling, and we actually think that there's many more Earth-sized planets than there are, let's say, Neptune-sized planets, right? So this would actually be filling very, very much so. Now, I said many of the features that we know already I mentioned, that we probably have more planets than stars in the galaxy. And you have to think a bit and reflect about this. There's more planets than stars in the galaxy. I think it's amazing, actually. Yeah. The most common planet types are Earths and super-Earths and sub-Neptune, so there's less giants than there are small planets, which is not surprising. Usually nature is able to build more small things than big things. There's many multiple systems around low mass stars, and I mentioned this already when I was discussing CARMENES. And one amazing thing is that even the closest closest star to our solar system has a planet already, more than one, like Proxima b, which is a very nice one. But besides all these things that we know, we have a number of outstanding questions that we haven't answered yet. And I have a couple of examples here. Many hot Jupiters have densities that are way lower than what models can predict or can explain. So we have planets with radii above 2 Jupiter radii, and this is the tail here, and this is planetary density versus planetary mass. So this tail here is really difficult to explain, and there's a few models that have been put forward with very fancy physical mechanisms that may explain this, but still not clear. There's no clear answer yet. So the reason why there's such puffy planets sometimes remains a mystery. And actually the first transiting planet found, which is HD 209458b, is in this region. So the first one was already sort of anomalous, if you want to say it this way. And now many people are working on some definition, not some definition, but the determination of a transition between rocky planets and gaseous planets. So at what mass planets stop being rocky, so mostly high density with a thin atmosphere, and start being gas-rich, let's say Neptune type. And this is the so-called cosmic shoreline. So many people are working today in determining this cosmic shoreline, which is the separation between gas-rich and gas-poor planets. By the way, our Earth is gas-poor, right? Compared to Venus, for example, which would be a little bit gas-rich, or Neptune. So it's not clear yet. So there's now research being carried out to determine at what mass this happened. It seems it's about 2 to 3 Earth masses. Below 2 to 3 Earth masses, planets are usually rocky. And above, there starts to be some planets that are not rocky, but they have some gas in them. And now, I think it's for the benefit of Salvador here. I mentioned that astrometry will also be, let's say, is also a very good indirect detection method for exoplanets. Now, there's a major thing coming up, which is Gaia, and Gaia DR4, the data release 4, which will release epoch astrometry for many, many millions of stars. And this will mean that there will be also exoplanet detections. So there was a very recent paper by Lammers and Wynne, and this is the plot they show. This is the same plot I showed before, the ones with these blue and green symbols. And all these other is the result of a mock catalog they have produced, trying to see how many planets Gaia will detect in the parameter space. You see here, DR4 mock, this is these maroon ones, and Gaia DR5, this is the black ones. And it's only plotting planets with properties better than 20% in terms of relative error. And you can see that I was saying that we will have 6,000 planets. Now we have 6,000 exoplanets discovered. So Gaia DR5 will probably, most likely, discover 38,000 or some number like that. And even with DR4, the number is about 2,000 planets, which means that this will be increasing by just like that by 50% the number of planets. Now, not everything is so super nice because there's going to be some contamination. Unresolved binaries with similar components are really difficult to tell apart from planets there because what Gaia measures is the photocentric motion. So if you have two stars that are very similar in brightness, the photocentric will move only very little, which is the ratio of this proportional to the ratio of the two luminosities. And this will be not super bad, but there for FGK stars, which is about 20% contamination, but it's going to be a big concern for M-dwarfs, where contamination factor will be probably about 50% or so. So this will mean that we'll have to invest lots of telescope time trying to tell apart bona fide planet signals from those that are coming from similar mass binaries or similar brightness binaries. There's going to be a major task for everyone there. So there's very likely there's going to be a catalog of potential planets from Gaia, but there's going to be a confirmation job that will have to be done later on. Now let's go one step more into how we do. Now I discussed how we measure bulk properties of exoplanets. So what if we can also measure the chemical composition, detailed chemical composition of those exoplanets? And this is what we do in exoplanet spectroscopy. We're talking about transits and occultations. Transits is when, as I said, the planet goes in front of the star. Then what happens is that there's a ring of atmosphere of that planet, and the star shines through this ring of atmosphere, and therefore it imprints the spectrum of the chemical components that are on this atmosphere, actually. And this is what the so-called transmission spectroscopy. And then there's also another way of getting information is that from the emission of the planet itself, which also contains information about the chemical compounds. You can see, in the case of emission, it needs to be only very hot planets, because otherwise we don't have enough light to work with. But as you can see here in these plots, this gives you information on different features in the spectrum that are related to chemical compounds, molecules on the atmospheres of these planets, right? And so this has been used a lot, and let me just show you real quick how this works. The main, I'd say the main thing responsible for the strength of the signal of transmission spectroscopy is the thickness of the atmosphere, the size of the atmosphere, and how this size compares to the bulk size of the planet. So the larger the ring is, the bigger the signal will be, right? And it can be worked out, it's very easy, but in the case of a hot Jupiter, the signal, typical signal of, let's say, transmission spectroscopy measurements there with the molecules and so on is of the order of 100 parts per million. Remember that I said that the transit was about 1 to 2% depth, and we're talking now that these depth variations to see the spectrum have to be about 100 ppm depth or so. So it's 100 times less. We have to be super precise measuring those depths to be able to get the spectrum. In the case of the Earth-Sun, and that's really depressing, that's less than 1 part per million. This is way beyond our capability today, even with the James Webb Space Telescope, and I'm going to address that. And in the case of an Earth and an M-dwarfs, we're talking about the typical features that we have on Earth, on an Earth-type planet or on M-dwarfs are of order of about 10 parts per million, which means that this is the precision we need to measure the transit depth with. Yeah. So this is done a lot, and now we are living a golden era of these measurements with JWST, because we have spectra that look like this, transit that look like this, which is amazing, actually. So this is about, you see a 2% depth transit, but we can measure the depth of the transit to a precision of order of several tens of parts per million. So now I'm going to launch a video here, and you see here on the top right part, this is the wavelength of light of this specific transit light curve. This will be changing, and then with your own eyes, you will see how this transit gets deeper when there's some absorbent in the atmosphere. Right? When there's more absorption in the atmosphere, of course, the ring of the atmosphere around on the planet will actually get opaque, and therefore the transit will be deeper. So, okay, I'm going to launch this here. It works because it's online, and then just pay attention and see where and look at the signal of an atmosphere with your own eyes. Okay, let's go. Oh, sorry, I have to do this. Did you see it? Can you see? Can you read off the wavelength as well? There you go. Right, so it's actually, you see the transit going slightly deeper, and that's because the planet at that wavelength is actually bigger. And it's bigger because there's an absorbent in the atmosphere. And that absorbent is actually CO2, so carbon dioxide. You can see here, this is the actual spectrum of this exoplanet, WASP 39b, on a broad wavelength. We're now observing, remember that we were observing from 3-something micron all the way to 4-point-something. So we saw this huge feature here, this huge feature that is caused by, as you can read off here, is CO2. Right? And you can see other gases as well. There's evidence for carbon monoxide, SO2, water vapor, sodium, potassium, and so on and so forth. There's a lot of this is what we call retrievals. So we actually try and see which are the molecules that can explain, a combination of molecules that can explain the observed spectrum. And as you can see, this is an easy one because it has a very strong CO2 feature and so on. But there's the possibility of determining the presence of many chemical compounds on the atmospheres of these planets using this technique. Now, what are the open questions in this field of exoplanetology, let's say, or understanding the atmospheres of planets? Well, there's a big outstanding question that there's been a lot of effort put in answering, and is, do rocky planets around M dwarfs have atmospheres in the first place? So have the atmospheres or the volatiles around in these atmospheres been able to survive the high activity phases of the star? You know, the M dwarfs can be very active. They have flares, they have particle emissions, they have a strong XUV and so on, and this can evaporate the atmosphere and get it, and the planet can lose it forever. And there's a big JWST DDT, so the Research Discussionary Time program, to try and answer this. 500 hours of JWST, which is a huge amount. And this is, and you can say, for now, not looking good, actually. And you can see this plot, this equilibrium temperature of the planet, and this is this ratio of the day temperature to the maximum theoretical temperature, because the way this works is that if there's a thick atmosphere, this is going to be very efficient at redistributing heat. So the night side of the planet will also be hot. If it's a bare rock, it's going to be a very hot day side and a very cool night side. And this is the measurement that we can do here. And as you can see, this is full heat redistribution. So you would expect maybe some thick-ish atmospheres here. This would be like Venus-like planets. And most of the observations are up there, which are pointing at bare rocks. So the planet is being completely bare of an atmosphere. So only the rocks themselves, except for maybe this one. But you see, this is in light color, and it seems that the observations have to be reprocessed. So it might end up being up there as well. So maybe the main conclusion from this is that there doesn't seem to be exovenuses around M dwarfs. So no thick atmospheres on planets around M dwarfs. And this is not very nice, actually, because it's not looking good for the thinner atmospheres either. Anyway, this is one of the things that are being done as we speak. And the other thing is that you probably have heard about this live detection on exoplanets. This was about this last summer or so. K218b, two chemical compounds that are called DMS and DMDS, which on Earth are usually associated to life processes. This is not a rocky planet. This is what the discoverer mentioned. The name that the guy gives is Hydrogen world, so hydrogen ocean world. No one knows whether this world has oceans in the first place. But anyway, there were some early claims of water that turned out to be methane, and these claims of DMS and DMDS are not solid. So it's not clear that there's any chemical compounds on this atmosphere of this planet that are anything related to this, or even the detections of the compounds are not secure, which means that even, and then this is not secured, and the interpretation of these compounds as the byproducts of biological activity are even less secure. So it's really not let's say, there's no consensus in the community by any means. So there's usually a lot of critique about this. Now, the Ariel mission will take this also to a new level, meaning that we will now explore thousands of planetary systems at once. So it's going to be same thing that James Webb is doing, but then specifically targeting exoplanets. And this case is a mission that will be launched in late 2029 and work for about 3.5 years or so, and idea to get an idea of the chemical diversity of exoplanet atmospheres. Now, real quick, my specific work that I do here is to try and understand what are the limitations that the star itself puts on our ability to find and characterize planets. Because as you know, stars are active, they have star spots, and they limit our ability to get to the best precision of the instruments in terms of radial velocities and also transmission spectroscopy. So what we are finding is that it's a blocking, let's say, factor. Understand the star close enough so that we can push our techniques to the next level to find these exo-Earths. So we know that the stellar activity affects planet detections with radial velocities where the instruments are performing better than our detections, let's say, which means that the noise limit is not set by the performance of the instrument itself, but by the variability of the star. And this is what we're trying to measure. And the same thing with transmission spectra, where variability of the star can actually wreak havoc on our ability to get atmospheres. For example, This one is a JWST transit, and there's two models. One is unocculted star spots. The other one is H2-rich atmosphere, and they're indistinguishable. So it could either be one or the other. And now we have to understand the stars much better than we do now to actually make progress along these lines. And I don't have time to discuss this so much. This is an ERC, a European-funded project. This is the one I'm leading. It's called Spotless, to try and get to RV precisions of order of 10 centimeters per second, and then to also to be able to see transmission spectra at the level of 10 parts per million. So now we know the answers to these questions, whether there's planets out there. Yes, there are many. How they form and evolve, probably. We will learn with PLATO and with Ariel. What are they made of? Same thing, JWST, Ariel, and PLATO. And now the next thing is, are they habitable and are they inhabited? Right? And we are not too far from making this next revolution in humanity, right? Because after the Copernican revolution, well, we actually realize of our place in the cosmos on a physical scale. This would actually be our context in the living universe, how rare or common our own planet may be. And to do this, let me just briefly mention that when we talk about life, we usually tend to define the so-called habitable zone because we associate life on a planet to the presence of liquid water on a surface, let's say. And this makes us define this habitable zone, this shaded region here, which of course varies in location, in orbital distance, depending on the mass of the star, right? So a small mass star, you have to get much closer in to actually have the same temperature. And the regulation here is provided by greenhouse gases, mostly CO2. CO2 is the thermometer of the habitable zone, which makes it wide enough for us to be here. So of the 6,000 exoplanets that we have right now, there's 29 that would meet the criteria of being potentially habitable, meaning that they have the right size to be rocky, and they have the right distance from the star to be able to sustain liquid water on the surface. So it's 29 out of 6,000. And the reason is that it's not because they're super scarce, it's that because they're difficult to find. Right? And most of these planets are actually orbiting M-dwarfs, which means that who knows whether they actually have been able to keep the water inventory. Now, then what is there for our future is try and see what kind of molecules these atmospheres of these planets, if they're there, may have, and whether these molecules are indicative of the presence of life on the surface. And these are what we call biosignatures. So combinations of gases that cannot be explained by any other means but the presence of life. So no explanation from abiotic sources. And so this is, by the way, this is the Earth spectrum, Earth emission spectrum. And you can see here all the molecules, relevant molecules like water vapor, O2, O3, CO2, methane, which are there. And these are actually giving information that we are here, that there's a biosphere that is active on the surface. I said that it's not looking good for JWST, so even in the best case scenario of an Earth orbiting an M5 star, so a very late type, the typical signatures of the relevant gases are of order of 10 parts per million, and that's beyond the capability of JWST for most cases. So it's very unlikely that JWST is able in the future, even now or in the future, to find biosignature gases on Earth-like planets around M-dwarfs, let alone around sun-like stars. Not a chance, right? There are some possibilities for the near future, and that's an instrument called Ristretto on the VLT. There's also a future instrument on the ground called Andes on the EELT for the 2030s. So these instruments should actually allow us to maybe take a glimpse about on the existence of atmospheres and maybe some chemical compounds for very, very, let's say, specific targets. That would be the best of the best, let's say. So that could be actually something that could make a difference. For example, Ristretto could be able to characterize the atmosphere of Proxima b if the atmosphere is there. No one knows, right? So at least there's some hope that from the ground and in the 2030s, there will be enough technical capability to start seeing what can be done in terms of bioindicators on some of these planets. And now the hopeful future is for missions like HWO, Habitable Worlds Observatory, or life from this is NASA and this is ESA or Europe. And these are missions that are aiming at the direct imaging of exoplanets and the acquisition of a spectra of those exoplanets by different techniques. So in one case is coronagraphy, so just an artificial eclipse of the star, which you can see in the video there. And this case is nulling interferometry, so these are techniques that are being now proposed. And the idea is to get actual measurement of the planet itself and the reflected or emitted light from the planet. Now, this is the very good news. The bad news is that if everything goes well, these are missions from the decade of the 2040s, maybe in the 2050s. That really drives me mad. But they're very expensive, of course. So that's what we have. So, just my second to last slide. This is there is a lot going on exoplanets, and you can see that by the number of missions, experiments, telescopes, instruments that are now in operation and being built. So both on the ground and in space, there's missions that are addressing exoplanets. Some missions are specifically built for exoplanet research, like PLATO and Ariel, and AWO and LIFE. And there's also lots of infrastructure on the ground, telescopes and so on, whose main objective is actually to observe and characterize exoplanets. And as I said before, way into the 2040s, probably into the 2050s as well. So if you guys want to work on exoplanets, there's going to be facilities there working for you in the next 2 or 3 decades at the very least. So what we're aiming at, and this is my last inspirational slide, I'm sure you all know this. This is the pale blue dot picture from Voyager 1 at 6 billion kilometers distance from the Earth. So this is a picture of the Earth, and Earth is actually 1 pixel on this image. So the idea that we have now for the next upcoming decades even is to be able to actually get pictures of pale blue dots and to try and understand what the atmospheres are made of, and maybe we're lucky enough to see some indications of chemical compounds that can be related to life. And this would be a groundbreaking result, not only for astronomers, not only for scientists, but also for humanity as a whole. I think it's very transformational. All right, so I'll stop here. Thanks so much.
Gracias. Muchas gracias. Empezamos con las preguntas en el auditorio. ¿Alguien quiere hacer alguna pregunta?
Thank you very much for your talk. It's very nice, my question. So about the PLATO mission, what could be the difference in the strategy to observe in terms of cadence or exposure time to discover this kind of new exoplanets, more similar to the Earth?
Well, it's about, the strategy there is just to have a wide field, let's say, and have the highest duty cycle possible, which means integrating as much as we can before reaching saturation and then read off, right? So this defines how long you integrate because you want to sample some specific interval of stellar magnitudes. And then with that you maximize, let's say. So in the case of Kepler, these were faint-ish stars or faint stars. In the case of PLATO, these will be a lot brighter stars. But the telescopes are also smaller. Kepler was 1 meter, telescopes here about 30 centimeters or so. So that's the strategy. And then there's also an input catalog, which defines which 250,000 stars are going to be downloaded. It's not the whole frame that is downloaded. It's only the so-called imagettes around its particular target, and those targets will be pre-selected beforehand. So it's going to be these imagettes, and this is going to be downloaded and then studied. I'm not sure whether this answers your question, but okay. Yeah.
¿Alguna otra pregunta?
In which band does the CHEOPS mission is observing? And about the noise in the transit signals, how do you know which part of the signal is noise and which is the actual signal? And when you have these different waves or the difference between the signal and the noise, how do you clean the data?
Yeah. Okay. Firstly, the CHEOPS mission works in the visible, and it's a sort of a reddish band, but it's pretty broad. So it's like a VR filter, Johnson's V plus R, something like that. So it's pretty broad because we want to maximize, minimize statistical noise error, right? So Poisson noise. Now, how we do it in the transits, yeah, the idea here, the transit depth is just defined. You take an out of transit part, and then you look an in transit part, and this will be transit depth. So we fit a model there. Typically a model which is very simple. The only thing that makes it a bit more complicated is because the star, as you know, it's not homogeneous. The brightness of the star is not homogeneous. I don't know, I have. And there's something called limb darkening, which means that close to the limb, the star is actually dimmer or fainter, and at the center is actually brighter, which means that the transit is not box shape. It has a specific curvature. And then we have lots of models there to try and fit this curvature. Whenever there's noise from different sources, if it's a stellar noise, we try to find a model. If it's a random noise or red noise or correlated noise, so we use models typically. And what people do these days is do some filtering, and some filtering is done with, for example, Gaussian processes. This is how we take into account these correlations between measurements there. So there's techniques to actually filter out some of the noise to make the observable better. But in principle, it's a very straightforward measurement because it's just this out of transits versus in transit. Yeah. But as we go to tens of ppms, then it becomes trickier.
Okay, we have a question in Zoom. Artem, please.
Hi, can you hear me well?
Yep.
Yes.
Yeah, thank you for the great talk, Ignasi. I do have a technical question that is related to transit spectroscopy. So JWST, like you said, JWST revolutionized the field with new data. But by doing so, we also learned about new limits on the technical side. And this is something that is a pretty new information, but you may know about technical challenges like offsets between detectors.
Sure.
And more recently, people have been talking about nonlinearities, the brighter fatter effect, and other things like that. Yep. So I was just curious about how, like, what do we learn from this, and do we actually intend to implement that in the future generation of telescopes? Do we need to, for Ariel, HWO, how long will it take to cross that boundary?
Yeah, thanks, Artem. Yes, indeed. Actually, 2 weeks ago, I was in Ringberg, and there was a workshop exactly about that, about understanding systematics with JWST data, and also stellar contamination as well. And yeah, as you look close into the data, of course, you find issues with it. And you mentioned offsets between detectors. You mentioned this brighter fatter effect. It's there. I'm quite optimistic that we can characterize these sources of error or uncertainty or offsets and then correct them. I think what I saw 2 weeks ago made me be quite optimistic. So I think we can find ways. Of course, as you say, this would be interesting to transfer into the new missions that they don't have the same issues. And Ariel will probably won't, because the resolution is lower and the whole design is actually quite different. So I'm quite confident that some of these will not be there, at least for Ariel. To me, the more worrying part, and is actually the part that I'm working on, is the effect of stellar contamination. So it's unocculted star spots, occulted star spots, in some cases flares as well. So these astrophysical signals that are now noise sources, let's say, in the transmission data, sometimes can be quite difficult to correct. And this, because they are more difficult to characterize, because each star behaves slightly different, right? So I always advocate for people to collect as much ancillary data, contemporaneous monitoring of the stars as we can, so that we can at least develop tools so that this stellar contamination can be removed or corrected somehow. So yeah, it's both, let's say, instrument issues, which I'm quite confident about, and also stellar astrophysical issues, which I'm also confident about, but I think they're even more tricky, I'd say. That's my take. Yeah.
Thank you.
Yeah, welcome.
Thank you, Ignasi. One question. You have told about a lot of missions observing exoplanets. What is the synergy between these missions? The
synergies, yeah. Yeah, it seems, in my opinion, there's overlap, but it's really not there. So there's some transit search missions, survey missions, and this is TESS, for example, here. There is Corot and Kepler there. There is transit follow-up missions to actually measure better some of the transits and validate some of the planets, like Cheops, for example. And then there's transmission spectroscopy missions, which are applying these to known exoplanets and observe them in transmission and so on. And then PLATO, as I said, one issue, Kepler mission was aimed at answering questions about demographics. So how many planets are out there and what kind of stars they orbit. But Kepler, the follow-up of Kepler targets is extremely difficult. Now, PLATO is there to answer questions about, so to produce a sample of planets that we can follow up a lot easier, and therefore deepen our understanding of those specific planet hosts. Not so much about statistics, but about acquiring precise data there. Yeah, JWST and Ariel are synergistic from a point of view that JWST, it's about low-hanging fruit, let's say. It's about going for the best planets and trying to understand this. In the case of Ariel, it's a statistical sample. So everything is there, try and have a popular, although a planet looks boring, we will observe it anyway. And then who knows, maybe there's going to be something, but that planet would never be observed with JWST because you can never convince a panel to give you time to observe a boring planet, let's say. So this is the synergy there. Of course, on the ground, the ground is mostly photometry and high-resolution spectroscopy, which you cannot do from space. So ELT, for example, or future, maybe, who knows, TMT or GMT, these are high-resolution spectrographs, which is a completely different way to probe planetary atmospheres, and a very powerful one as well. And it's going to be nice to see whether there's mutual agreement for the same planets, let's say, which is not always the case. And then there's a completely different, separate class, that's the direct imagers, either coronagraphy in the visible or interferometry in the infrared. And this is completely separate from everything else. And they're also quite complementary. What you can get from reflected light in the visible is not the same you can get from, let's say, emitted light in the mid-infrared. So in the mid-infrared, you can get the temperature of the planet directly, the radius of the planet, and you can get some chemical compounds that have strong features there, while in the visible, you have other features, let's say. So they're very complementary. Although I'm not very optimistic that humanity will be able to afford two of these big missions at a time, let's say. We're talking about 5 billion each, more or less. And that's 5 billion each. That's very expensive for NASA, given the current circumstances even more. And for ESA, yeah.
Another question here.
First, thank you for adding that slide there. The guidance.
Sorry.
I mean, astrometry is going to be very important in the near future. But there is something that you didn't mention, and because you included a radio telescope.
Yeah,
there.
exactly.
So there are more ways to do astrometry.
Yeah.
And they are also very promising.
Yeah.
So doing a radio astrometry, it's possible to detect planets, a lot of planets. Actually, some recent estimates show that probably a few or several thousand exoplanets could be detected using radio astrometry with the new telescopes that are being built, SCA and also NGBLA. But the second part, and this is something that I would like to ask, it's the interaction between, actually it's two things. One is the interaction between the planet and the star. Mm-hmm. So this is something that it's, I believe, a lot easier to do in radio observations.
Absolutely.
And also with very high angular resolution. That's why one of the main goals for these new telescopes is trying to do that.
Yeah.
One is that, and the other one is they detect directly the planets, because that would be probably the best way to measure the magnetic field around the planet, in the planet. Yeah. And this is very important for life.
Yeah, absolutely. I know you said it. In terms of detection techniques, of course, as many smart people work on this, they're coming up with different and more clever ways to do this, and radio astrometry is one of those clever ways. In the case you have a radio source to try and super precision observations, of course, yeah. And you are the pioneer in this, so yeah. There's a big field, a huge field now evolving. It's these star-planet interactions, There's LOFAR that has produced a catalog of potentially planet interacting systems. There is also SKA will be big there as well. So there's a lot of cross connection. Not radio, as you said, is good, but we have a paper accepted in Science, what should be coming out in the next weeks or so, where we see star-planet interactions in the chromospheric fluxes as well, in the visible, let's say, in spectra. So there are ways, and you see that because there's, the periods are the same of the period of the variability of this chromospheric emission is the same as the orbital period of the planet and different from the rotation period of the star. So there's connections there, all sorts of connections, and this is a field that is now booming, let's say, and I'm sure there's going to be a lot more. And measurements in radio and different wavelengths, polarization, many things that can be done as well. Yeah, there's a lot of potential, as I think, on these techniques using radio, both for detection and also for understanding star-planet interactions. Yeah, thanks for the point.
A couple of last questions, please. Gillen and then
I
Silvia.
have a short question. So, how certain is the late 2026 launch date for PLATO?
Okay. I think it's quite close to what it's going to be. I don't think it's going to be late 2026, but I think it's going to be early 27. But it's not going to be late 27, that's for sure. So everything is on track. The instrument, the satellite exists, and there's been pictures shown around, and it's actually already down in Kourou. And so it's getting ready for launch, yeah. But yeah, a slight delay it can be foreseen, but not a big one, yeah.
Mine is a very simple question. At present, we consider there are 6,000 known planets. How many of those, or what's a fraction of those that we have spectroscopy of?
Yeah.
Because that's much harder, and of course you were looking into the future, but at present, what's the situation?
It's a bit more than 100.
Okay.
For 100 transiting planets, we
That's a
have
lot.
atmosphere. It's a lot, yeah. That atmospheres that are, let's say, thick enough and expanded enough that we can see the atmospheric features. I mean, it is maybe 150 or so, but that's already this number, yes, with some specific chemical compounds on all of them. There's a catalog of that you can go and play around which molecules have been found on different planets and so on. Yeah.
Thank you.
Yeah.
Okay, thank you very much. Let's thank
pleasure.
again Dr. Ribas for a very excellent talk. Gracias y hasta el próximo año.
Thank you. Gracias.
Entonces, ¿qué planeta es?